In the year 2600, Professor Olivia, a talented physicist, created a plan. The device of the times is named the time reflector. The principle of this device is to allow users to look back at their history through a reflective surface, without having to actually go back in time or interact with it. The core function of this device is to capture and analyze emitted light particles. One day, the professor decided to use this time reflector to review his work in developing the circular machine. When observing your past self, he discovered a calculation error. He realized that if this mistake could be corrected, can create a more efficient, more powerful time reflector. He was deeply interested in this, decided to write down the revised equation on a piece of paper and show it to Reflector. He hoped that his past self would notice the note and make the necessary corrections. To his surprise, his past self saw this corrective equation in the reflector and made changes accordingly, thus successfully creating a more advanced version of the time reflector. But this also led to an unexpected result. The version of the device Professor Olivia is currently using no longer exists because it was replaced by an improved model. This situation raises an interesting question. What if the improved time reflector was just because Professor Olivia saw it in the original device? That correction equation exists. So how could the original time reflector not exist at the same time? Is it because of the improvement of his own information sources? This scenario is an ontological paradox. This is a classic example of the famous bootstrapping paradox. It shows an infinite causal loop. Development of information surrounding an object or individual. This information cannot be traced back to an identifiable point of origin. This time travel setting leads to a closed causal loop. Some of these events or objects played a key role in their own origins. If there is no subsequent self-involvement, this story cannot be established. This is just one of the many paradoxes surrounding the concept of time travel. Continue to delve deeper into this topic. We'll find it getting more and more confusing. However, there is actually a way, without destroying the order of the universe. Achieve this goal. Every moment, we are all traveling from the past to the present and into the future. Time always flows in the same direction. At no point does it stop or reverse. In fact, time always only moves forward. The existence of time means that every moment is unique. No moment will be repeated. When we carefully observe every time in the universe, we will find even an experiment cannot be an exact replica of another experiment. From Newton to Einstein, from Maxwell to Bohr, Feynman again. The laws of physics appear to be equal in both directions of time. In simpler terms, according to these laws, whether time goes forward or backward, things don't work differently. Whether it's the past or the future, systems that obey the laws of physics should all behave the same. But in our daily experience, time seems to only move forward. Then the question comes, why time seems to have a specific direction, despite the existence of time-centered physical equations? Not everyone understands this. Although Albert Einstein, in his 1905 special theory of relativity, proves that time is an illusion relative to the observer. When you are in space and time, you will always follow the same laws of physics. Fundamental constants remain constant in space and time. The concepts of distance and time that we measure with signs made of atoms always have the same length. And test equipment like the clocks we make will consistently show time passing at the rate of 1 second per second. For all observers, whether from the perspective of quantum theory or Einstein's general theory of relativity, there is no exception to this. In order to understand this concept, we first have to understand injury and time symmetry. Damage can be described as a measure of the disorder or randomness of a system, or a measure of energy or chaos within an isolated system. In other words, in a closed system, the process naturally tends to proceed from a lower injury to a more orderly state. A relatively high damage, less organized state transition. Melting ice is a perfect example of injury, because the molecules in ice are arranged in an orderly manner, and when it melts, molecules become freer and more disordered. We can say that the damage to the system has increased. Injury is one of the few processes that time is irreversible. Time symmetry can be easily understood using this analogy. If time is symmetrical, real-world video plays forward or backward. All look equally real. In video, if we see a pendulum swinging with no resistance or friction, whether this video plays forward or backward, they all look the same. This shows that the system is symmetric in time. But in real life, the pendulum will eventually stop. This is irreversible in time. When moving forward, the kinetic energy of the pendulum gradually dissipates as it increases. We can do this by looking at atoms, how molecules and objects are organized, to understand the direction of time. If we see the state of the world becoming more random, then it points to the opposite of the future. If we look forward along the arrow of time, can feel the future. At the fundamental level of the laws of physics, there is no clear distinction between the past and the future. Time is a bit like space. If you were in space, there was no real difference between up and down and left and right. You can only perceive things like up and down or left and right based on other objects relative to where you are. The laws of physics themselves do not distinguish between the past and the future. Time is not just a spatial dimension. It also involves the measurement of world separation. In the microscopic particle world, this is often expressed as a narrative. For example, kilometers per hour or meters per second. Most physical processes are considered to be time symmetric. This means that if we reverse the direction of time, the theoretical rules governing these processes remain valid, but on a larger scale. For example, in our daily life, time doesn't seem to be symmetrical. At a macro level, there is a clear flow or direction in time. Basic laws of physics, Newton's laws of motion, the law of universal gravitation, and the imaginary equation. Neither represents a specific direction of time. They are time symmetric, but there is one exception. Second law of thermodynamics. This law states that in an isolated system, injuries tend to increase over time. As I explained before, the increase in injuries is an irreversible process. Injury is one of the reasons why we can't go back to the past. For example, cold coffee and milk are mixed together to produce hot coffee milk. This process never reverses itself. After mixing coffee and milk, once the system reaches its temperature equilibrium state, will not decompose by itself. This state of complete disorder or maximum damage and its equilibrium state. There is no longer a specific direction that determines the arrow of time. This suggests that the flow of time we experience represents a non-equilibrium state. The fundamental challenge lies in understanding macro-irreversibility, how it emerges from an intrinsically reversible microscopic process. Physicist Arthur Eddington proposed the concept of an additional arrow of time in his work. Let's take a look at some of them. First, the thermodynamic arrow of time. The thermodynamic arrow of time is provided by the second law of thermodynamics. This law means that time is asymmetric with respect to damage in the system. Essentially, this can be used to differentiate between the past and the future. By measuring the injury, if the injury increases, the arrow of time points to the future. If injuries are reduced, the arrow of time points to the past. As time goes by, the injuries continue to increase. This largely determines the thermodynamic time arrow. Then it happened, the arrow of time in mantra learning. Our observable universe began with a known highly ordered state, the Big Bang. Since then, it keeps swelling as the level of injury continues to increase. The mystery is, why did the universe begin with such an orderly initial phase, the so-called low injury state of a big explosion? This question has to do with the cosmological arrow of time. It indicates the direction of the expansion of the universe. Modern cosmologists are trying to answer this intriguing puzzle. As Richard Feynman pointed out, only by transforming the mystery of the origin of the universe from speculation into a scientific understanding of the thermodynamic arrow, only then can we fully understand the arrow of time. The second law of time and heat can be seen as a consequence of the initial conditions of the universe. Without the cosmological arrow of time, all other arrow implementations are impossible. The arrow of causal time is evident in our everyday experience. Cause always precedes effect. For example, an egg cracks because it is dropped rather than the other way around. But at a basic level, physics shows no preference for the arrow of time. Information about a particle's momentum and position can be used to predict its future motion. It can also describe its past movements. But this does not mean that there were causes and effects before so. The concept of cause and effect on a macroscopic scale only becomes apparent when larger collections of particles are present. The perception of cause and effect can be thought of as the movement of heat lines. Quantum mechanical arrow of time consequences. And the arrow of time is a consequence of the second law of thermodynamics. Finally, the quantum arrow. According to the Copenhagen interpretation of quantum mechanics, quantum processes follow the time-symmetric Schrödinger equation and the time-irreversible wave function collapse. This means that although at the quantum level, time can be symmetric in time, but the observation process introduces the irreversibility of time. This shows that even at the micro level, the flow of time is not completely symmetrical either. Quantum arrow reveals connection between quantum mechanics and the macroscopic world, is one of the keys to our understanding of the direction of time flow. The arrow of quantum time is determined by the time direction of the system's wave function. This usually manifests itself during measurements, even though the measured state is purely probabilistic. A connection to the thermodynamic arrow of time may also be suggested in this case. When the observer perceives the exploration of the wave function, the quantum version of is actually observing the measurement state or its information entangled with the wave function. Therefore, the thermodynamic arrow of time is the increasing entanglement over time. Researchers found that even at the microscopic level, the second law of thermodynamics also states that injuries will increase in most cases, because our process of measuring information seems to create an arrow of time. In quantum systems, time reversal of time arrow is possible, because they are related or entangled and share certain information. In the absence of inter-system correlation, the second law seems to be broken. This highlights the subtle connection between quantum mechanics and thermodynamics. Time is essentially an arrow. It is governed by the second law of thermodynamics in macroscopic motion. Injuries increase over time. This means the system starts with a low-damage state. Initially, the intricate interactions between particles in the system became extremely complex, so that the final state is extremely unlikely to return to the initial state. Therefore, it can be said that these initial conditions are the cause of this irreversible belief. Everything that has happened since the formation of the universe is an upward narrative. The arrow of time is only in the direction from lower injury to higher injury, not intrinsic to the most fundamental laws of physics. Rather, it exists because certain periods of our universe are conditioned. Once we understand that systems will become more disordered, why does it have low damage status in the first place? For us, why does time extend in a noble way from the past to the future? Imagine, received a letter from my future self. Details a series of events and decisions you will make over the next few weeks. You consciously change your behavior to deviate from the predictions of this letter, but soon realize that the changes you made were exactly the same as the altered version of events in the letter. The paradox here is whether this letter accurately predicted your future, or do you try to satisfy them by actually violating its predictions? This case explores the complexities of free will, determinism, and the mysterious connections between past, present, and future in the arrow of time. The scenario described is an example of a causal loop or fatalistic paradox. In this case, there is a cyclic relationship between events. The letter describes events from the future and the person's actions, because this letter seems to predict events. But this man tried to change these events, ultimately led to the results predicted in this letter. This forms a cycle. Cause and effect are intertwined. Back to our previous scene. At the beginning of this video, Professor Olivia creates a paradox. You will see, the paradox lies in the fact that the improved time reflector owes its existence to the original version. It eventually replaces the time loop, creating a situation that is difficult to determine. Clear source of information. information needed to improve time reflector past from future to past. But there is no obvious starting point. This is a circular guidance paradox with no clear missing point. It suggests a scenario in which the event does not exist, a clear sequence of cause and effect, but forms a closed loop with no identifiable beginning or end. This paradox is a fascinating concept, often discussed in discussions about time travel. Time travel is a topic we need to discuss next, because it seems like you can actually, without causing problems or what we call paradoxes, it is impossible to go back or forward in time. Look at this hypothetical particle. A team of quantum physicists in a laboratory sent a particle to the year 1800 to observe conditions. But when the particle reaches the past, it interacts with historical figures, change their behavior, which triggers the butterfly effect paradox. Even small disturbances in the past can have significant consequences in the present and future. Changed behavior results in the creation of a new reality in the timeline. To solve this problem, they send another example to the past. But this sets in motion the topographical correction paradox. Every attempt to fix the timeline results in more changes. This results in an infinite cycle of corrections and changes. Feeling stuck, they try to send messages to their past selves to avoid the original time travel experiment. But this leads to the paradox of information divergence. This information creates a split in the timeline. Different versions of time coexist. Now, the lab is the center of temporal uncertainty. Scientists are trapped in a web of paradoxes. The once simple concept of time travel reveals its complex and unpredictable nature, causing scientists to question the consequences of their exploration. Time travel is a curious journey full of unexpected surprises. Challenging our understanding of time paradoxes really shows us the complexity of traveling through time. As our understanding of time travel grows, we started to think about why these paradoxes occur and whether we can travel through time without incurring these complications. Classical dynamics allows us to predict the position, trajectory, and velocity of an object based on its specific time. This applies to various scenarios, from the movement of the moon in the sky to the specific location where the rocket will be launched to Mars, even touching the ball in flight. Einstein put forward this idea. Massive objects can warp space-time. The larger the object, the greater the distortion of space-time it produces, the greater it distorts the space around it, giving rise to the phenomenon we call gravity. This concept opens the door to possibilities such as time travel and time loops, where time can exist in both the past and the future. However, these two ideas seem to be contradictory, leading to a paradox. Germain, a mathematician at Stockholm University, Tobar aims to reconcile these theories and implemented this mathematically. So what exactly did his team find? Imagine this scene. You went back in time to stop the first person from getting COVID-19. If you succeed, a paradox will arise, because that removes your original motivation to go back to the past. Even if you block zero good patients, you could end up getting infected yourself and become a zero good patient, or someone else. No matter what you do, important events will adjust and recalibrate around you. So despite your efforts, epidemics still happen. Give your younger self the motivation to stop it. Try to create a paradox. Time always adjusts itself to avoid any inconsistencies. Mr. Tobar's mathematical research shows that free will time travel is logically possible. His calculations show time has a way of correcting itself. We used to think of time as a highly sensitive and complex system. Even a small change in the past can have a significant impact on the overall outcome. However, Mr. Tobar suggested, time or nature itself may be more elastic than we think. This raises questions about free will and destiny. If we can't change the past, what does this mean for our ability to make choices? If the time automatically adjusts, do our actions really have consequences? Researchers at Los Alamos National Laboratory, using quantum computers to simulate time travel, they find that the butterfly effect does not exist in the quantum realm. when they transport information or quantum states into the simulated past, even if one of the states is significantly corrupted. Surprisingly, when all states return to the present, they look basically unchanged. This shows reality is self-healing in the quantum realm, and small changes in the quantum realm do not have much impact on the present. So on the quantum scale, the butterfly effect does not seem to exist. Furthermore, Mr. Tobar's work shows that, even if we go back in time and results, any major changes will not significantly alter the present or future, at least as far as we currently understand. If the concept of time self-adjustment itself and the non-existence of the butterfly effect proves to be incorrect, we can still observe a form of time travel in real life. According to Einstein's theory of relativity, through the phenomenon of time dilation, when an object is moving at a significant fraction of the speed of light or is in a strong gravitational field, time will dilate. In these cases, the time of an object that is moving or affected by gravity is relative to the observation of a stationary, or for objects in a weaker gravitational field, will appear slower. This means that time is not uniform throughout the universe. It can be stretched or compressed depending on conditions. In China, although this is not the traditional time travel we usually imagine, but it's a scientifically proven effect, demonstrates the plasticity of time under certain conditions. The movie Interstellar, there is a dramatic example of time dilation in which Matthew McConaughey and his crew land on a planet near a black hole. Due to the huge gravitational influence of black holes, time slows down significantly for astronauts on Earth. So 1 hour spent on Earth is equivalent to 7 years spent on Earth. The moment the astronauts returned to Earth, they were shocked to find that Matthew, NCC's daughter, is already old. This phenomenon demonstrates the wonder of time dilation. During space travel, due to the relativistic effect, astronauts age much more slowly than on Earth. This phenomenon solidifies the relativity of time. In different gravity environments, the flow of time is different. However, this fluidity of time does not allow our consciousness to return to events that have already occurred in the past. In theoretical physics, there are some hypothetical concepts, such as closed time curve. These concepts are often related to certain knots in Einstein's equations. These concepts involve complex conditions such as traversable wormholes or rotating black holes. But these only exist at the theoretical level. In fact, there are huge challenges both conceptually and practically. To date, the scientific consensus is that existing physics does not provide a method. Let's go back in time in the way time travel is in our everyday understanding. To understand these theories, especially when it comes to the possibility of going back in time, we can think of time as a river flowing in one direction. Stand on the bank of the river and watch the water flow past you. The progress of the river represents the passage of time. We can observe the flow of water and feel its flow, just as we feel the progression of time in our lives. As the river flows, it carries various objects forward. These objects symbolize events experienced, even the particles that make up our universe. If we try to swim upstream, return to some earlier point in the river, we will find it incredibly challenging to go against the power and flow of a river. In the same way, going against the time of injury control, it's almost impossible to go back to the past, although we can have memories and records of the past. But the actual flow of time keeps pushing us into the future. Just like we can't change the flow of a river, we can't change the direction of time. Time carries us forward along its ruthless tide. To better understand time, think of it as an unwavering line, river flowing in one direction. This metaphor helps us grasp the irreversible nature of time and the challenges we face when we try to travel against the flow of nature. Start with Aristotle. This ancient Greek philosopher believed that time was a fundamental aspect of nature. He defined time as a measure of movement and change. In Aristotle's view, time is closely connected with the material world, dependent on movement. He believed that time exists only in these changes, emphasizes the close connection between time and the unfolding of the universe. Our journey through time takes us to meet the influential 17th century French philosopher René Duarte. Duarte sees time as an essence. He believes that our perception of time arises from the workings of the mind. Duarte emphasized, our inner sense of duration is what we, the basics of understanding time, highlights the subjectivity of our experience of time. Move forward. We meet the 18th century German philosopher Immanuel Kant. Kant explored the relationship between time and our perception of the world. He believes that time is a necessary framework for our thinking about the world. Dare to organize our sensory experiences. Enable us to develop a coherent understanding of the external world. 19th century German philosopher Friedrich Nietzsche offers a unique perspective on time. Nietzsche viewed time as a human construct, affects our understanding of reality. He believes that our perception of time is influenced by cultural and social context, challenging the traditional concept of linear time, and emphasizes the subjective and interpretive nature of time experience. Fast forward to the 20th century. We meet German philosopher Martin Heidegger. Heidegger delved into the concept of time. He argued that our understanding of time is not limited to measurement or continuity. Heidegger proposed, time is the basis of our existence, shaping our existence in this world. For him, time is not just a linear process, but the complex interplay of past, present, and future through our contact with the world. Now we come to the concept of simultaneity relativity. As Einstein proposed in his special theory of relativity, the effects of time dilation challenge our traditional ideas about simultaneous events. When an observer is moving at high speed, the moment he experiences may not exactly correspond to what another observer would experience in a different reference play. This phenomenon prevents us from unambiguously determining the same time at two different points, thus introducing a confusing ambiguity. What's more complicated is, when we observe objects or people, the light that reaches our eyes actually carries information from the past. This introduces a time lag between what actually happened and our perception, therefore. The current concept actually becomes a partial concept, a time bubble that surrounds us. Even our observations of distant objects are affected by this time delay, because the light from those celestial bodies takes a lot of time to reach us. Modern physics challenges traditional view of linear flow of time, revealing the dynamic interplay between gravity and the passage of time. According to the general theory of relativity, places with strong gravitational fields, time will slow down. This means that in space where gravity is weaker, clocks move faster than on Earth. This gravitational time dilation not only affects time, it also affects physical behavior. For example, machines in space may operate at higher frequencies. Biological processes like flower blooming may also occur more quickly. The fundamental reason for this time difference lies in the impact of massive objects such as planets and black holes on the structure of space-time, distorting space-time, causing stretching or distortion of time between different gravitational field positions. The difference in the passage of time can be measured. When we think deeply about the nature of time, we face many controversial issues. These questions challenge our understanding of reality. Is time really passing or flowing? Is it a universal phenomenon or a local structure? The interaction between gravity and time, how it shapes our perception of the universe. These questions drive us to explore in depth, inviting us to delve deeper into the ephemeral and mysterious realm of existence. I stop and don't do anything. Feel the passage of time. This is the familiarity and intimacy of time.